Okay, so let's start. So good afternoon, everybody. So let's start the next set of lectures by Jérémie Bec. So he's going to talk about statistics of turbulent flow. So, yeah,
okay.
please go.
Thanks. It's okay. You hear me because I don't hear the microphone is working. It's fine. Okay. Okay. So thanks a lot for the invitation. So I'm pretty happy to give this lecture. So I have prepared some slides, but if you prefer Blackboard, I can do also things on Blackboard. So you maybe for some stuff it might be easier to follow on Blackboard. But today I will show you movies, so it will be easier with presentation. So you just let me know if you prefer Blackboard, so that you have time to think about formulas, etc. I will do it on Blackboard. Okay. So the aim of my lecture is to do some bridges, to draw some bridges between the physics of turbulent flows, questions which are more related to engineering purpose for how to use what is known from the physics of turbulence to model turbulent flow for engineering purposes, and then the mathematics also of Navier-Stokes equation and turbulence. So somehow where we stand concerning actual mathematical results. So today, my first lecture will be about explaining what is called the turbulent flow, okay? Explaining a bit also what are the different viewpoints on how to describe turbulent flows, and to give you some ideas about the phenomenology, the scales, the cascades, etc., the self-similar assumptions that are used to describe turbulent flow. So of course, don't hesitate to interrupt me if you have any questions, or I'll be very happy to answer. So yes, this is the outline I've just described. So where and why do we observe turbulent flow? What are the various views of physicists, mathematicians, and engineers on the problem of turbulence, and the notions of, the basics of phenomenology of turbulence. So I like to quote this. So I don't know who is this G.K. Vellis. He's not very famous, but I like this sentence. So basically, turbulence is like pornography. So it's hard to define, but when you see it, you know it's turbulence. So the one of the first ideas of turbulence, and actually it's the person who coined the name turbulence, was Leonardo. So and this is one of his famous sketch that you see here, where basically he was already able to understand somehow that when you put, so you see it's you have a tank here, a reservoir, and you're pouring some waters in it, and what you see is that you have eddies of different sizes which are forming. So already had these ideas of eddies from turbulent size, from different sizes, and he coined the name turbulence, so in Italian turbolenza, which is related to the motion of crowd. So turbulence is coming from turba in Latin, which means crowd. So it's like the motion of a crowd. Okay. So basically, there are many situations where one has to deal with turbulence. So it ranges from various cases, from basically industrial applications, so engines, wakes of airplanes or cars, dispersion of pollutants in the atmosphere, up to natural settings. So at the scale of oceans, so for instance, for plankton transport in the ocean, for cloud formation, so which is quite important in order to understand how to predict climate or meteorology. So to understand how the turbulence of the airflow is changing the property of the clouds, lifetime of the clouds, the kind of droplets you expect to see, and of course at astrophysical and cosmological scales, where any flows at that scale is turbulent, by sure. So the common feature of all these things is that they are more or less described by the same equations. So of course with different scaling. So there are other kind of turbulence. So this is what we will call some hydrodynamical turbulence, in the sense that it's the equations of motions are those for the motion of a fluid. But now you have different kinds of turbulence, which are also which have been more on fashion for the last years. So one is the case of supraconductors, where you have vortices appearing, and these vortices can have a chaotic motion, which is very closely related to what we observe in some turbulent flows. Then there is also this active-like turbulence, which is turbulence of bacteria. So bacteria, when they have an active motion, they tend from time to time to self-organize and to create some correlations in their motions at larger scales, which are again described by turbulent notions. So of course, something related to applications of important applications, and in particular fusion plasmas and tokamaks, where basically the plasma is tried to be maintained in a turbulent state in order to have all the right things happening and the right mixing between the different species, ions, etc. And the very large scales of the universe, the cosmological large scales. So basically, you have to imagine that each point here is a galaxy. So we're looking at very large structures, where again we have this almost chaotic and self-similar densities which are appearing, which again has something to do with turbulence. So I will not talk much about these cases. I will talk a bit about these things in one of my lectures. But here, to start with, I will focus on fluids, on fluid turbulence. So what is a fluid? So a fluid is something which is in a different state than solid. So fluids are including gas and liquids. And basically, it's something which is usually described by hydrodynamical equations. So here, I will mainly focus on the incompressible Navier-Stokes equation. So I guess that most of you know what I'm talking about. So incompressible in the sense that, so I have first an equation of transport for density. So I have a density rho, and I assume that this density is constant. That's what I mean by incompressible. So in actual situation, it means that I'm looking at scales, at velocity scales, which are much smaller than the speed of sound, in the sense that I don't see any density perturbation in my field. So if this density is constant, what you see is that the transport of density implies that the velocity field has to be divergence free. So that's what we call an incompressible velocity field. So divergence has to be zero. And then the next equation that you write is the equation which corresponds to the acceleration of a fluid element. So assume that in our fluid, we take a small element of fluid and that we balance the different forces that are acting on this fluid, on this element. And so what we get is that the time derivative of velocity, so it's a material derivative in the sense that it's following the fluid element in its motion, is equal to the sum of forces that are acting on this element. So the forces that we are typically considering, there is a pressure force, okay, so which is a gradient force acting on the fluid element. Some viscous dissipation, which is just proportional to the gradient, to the Laplacian of the fluid velocity, and then we can assume that we have some external forcing, some injection force. So you see, so basically this is the set of equations that we have. So we have one equation, this is a scalar equation, three equations, because this is a vectorial equation, so D equations in dimension D. So which means that we have D+1 equations, and we have D+1 unknown. So the unknowns are the D components of the velocity and the pressure. Pressure is closed by the divergence-free equation. So if you want, you can interpret also this pressure as a Lagrange multiplier, which is imposing the constraint of having a divergence-free velocity field. Or you can have yet another interpretation, is that in these terms, in the various terms, if you don't look at pressure, it could be that, for instance, this term is creating gradients. Okay, so there is this term has a gradient part. So it has a solenoidal part, a gradient part, and somehow this pressure is here to remove the gradient part that you put in the velocity field at each time step. Okay, that's clear.
So Jeremy,
yes.
I mean, sometimes I could also, I mean, sometimes one uses P as a pressure given by some equation of state, right, for the fluid.
Yes, so that's the case in compressible too.
For compressible, because it's incompressible, so then
exactly.
That doesn't fix.
Exactly. So usually, so now if you have a compressible flow, so you have, of course, the density is varying, so you have to account for for the continuity equation of density. Then here you have this term. So again, usually what you do is that you multiply by rho, so you have so that you have an equation for the momentum, and this equation is unclosed because of pressure. So you have either to prescribe some state equation for the pressure, or you have to add another equation for the density of energy, and then relate pressure and energy this way. So I mean, there are different closures for compressible flows. So here I will focus on incompressible flows. So basically, now if you look at these various terms, so these two terms, so the term which is this nonlinear term, which is coupling different scales, and this term, which is actually just a way to remove the gradient part of this term. Okay, so basically they are responsible for transfers between scales. Okay, so since they are nonlinear, they are coupling. So if you think about taking, for instance, Fourier transform of this equation, so the Fourier transform of this equation, so this term is linear, so it would just tell you how the modes associated to Fourier k to wave number k is varying. This term is also linear, so it's also again local in k space. Okay, but then this term, so since it's a product, so the Fourier transform of a product will give you a convolution. So which means that you have different scales, different wave numbers, which will contribute to what's happening at wave number k on which you're focusing. And this term, since it's coupled to this one, is again having the same kind of structure. So now, since so what do we mean by turbulence? So basically, turbulence means that dissipation is weak. Okay, and if you think in terms of scales, it means that at the larger scales of your flow, this term has almost no contribution because, for instance, viscosity is very small. So usually, how we measure, so we are in the turbulent state when the terms which are nonlinear, so those which are responsible for activating different scales, are much larger than the scales which are the term which is dissipating. And this is measured by a non-dimensional number that we call the Reynolds number, which was introduced by Reynolds himself, and which is the ratio between this term and that term. Okay, so when it's very large, it means that this is much bigger than that, so that you have these multi-scale things activated. And of course, when it's very small, it means that viscous dissipation is dominating. So, so basically, now you see that this term is like velocity squared divided by length. This term is like viscosity times velocity divided by length squared. So when we make the ratio between the two, what we get is velocity times length divided by viscosity. And this is the Reynolds number. So it's the typical scale of velocity at large scales, of course. The typical length scale divided by viscosity. And if you want, you can also see it as the ratio between the dissipative time. So the dissipation time will be L squared divided by nu, divided by the advection time, and the advection time is just L divided by nu, by U. Okay, it's okay. So basically,
sorry.
Yes.
Quick question, but what is the length scale in the problem?
It's the length scale at which you observe, okay, for instance. But I mean, I will talk about length scale almost during my whole lectures. So it will. This is just a quick overview. So basically. So for instance, if you look at scales at which you are injecting energy, so assume that this injection force has a given typical length scale and a typical amplitude, which is defining also a typical velocity. So then U and L are defined through the force. Okay. So now what I was saying is that when the Reynolds number is large, the flow is unstable and is becoming chaotic, and this is what we call turbulence. So, examples. So there are different ways one is getting a turbulent flow. And so a first mechanism to have this triggering of instability is when you have a boundary layer. So I took a movie from Johns Hopkins. So it's a numerical experiment. So what they want to mimic is a flow which is going through this kind of wind tunnel and then flowing over a plate like that. So the flow so this is how they mesh the thing. So the flow has some excitation coming from a grid upstream. So this is triggering some instability. Okay, so this is the instabilities that you see, and then it's touching the plate here, and because of the large velocity difference between the mean flow and the plate, on the plate you have no velocity. Basically, so these are the initial perturbations, and what you see is that you are going from something which is laminar at the plate, which with some transitions here, to something which is fully turbulent behind. So turbulent means that it has many scales which are excited at the same time. Okay. So another mechanism is natural convection. So this is also something which is, yes, please.
So in this Navier-Stokes equation, now this grad P will be an input, or it will be determined by this incompressibility condition.
So grad P is a part of the problem.
Okay.
And it's determined by the incompressibility condition. Okay. It's not an input.
Okay.
So in the specific case of a flow in a wind tunnel, actually what you impose is a mean gradient of pressure, but it's not really the dynamical pressure that is associated to your incompressibility condition. It's you can see more like an external force. Okay.
So in this case, how would I write P in terms of this U?
So maybe I can write the Poisson equation. It will be easier. Try to use small space. So basically, so we have, do you see if I write here? Do you see? It's fine. So you have divergence-free condition. And then you have Navier-Stokes. Let me do it just with Euler. It will be easier. So let me forget about the viscous term. So now, basically, I can take the divergence of this equation. Okay. So if I take the divergence of this equation, I have that the time derivative of the divergence of u, okay, plus the divergence of u grad u, and this has to be equal to minus the Laplacian of p. Agree with that? So now, if I want this, since I'm imposing that any time, any points in space, I have a divergence-free vector, so I have to have this equal to 0. So which means that I have now a Poisson equation, which is telling me that Laplacian of pressure has to be equal to minus this divergence of u grad u. So you see there is a non-local, so pressure is determined by velocity, and the relationship is non-local. Okay, so because one has to invert the Poisson equation. Okay, so this is in the fluid dynamics jargon, this is called Poisson equation for pressure. Am I answering your question? Yes.
The boundary conditions can be specified by hand.
Of course.
In this equation.
So the boundary conditions, I mean, it has to satisfy the boundary condition. And so typically the usual boundary condition when is getting for, so now for viscous solutions, so when I had these things, is a no slip boundary condition at the walls, which means that the velocity is 0 when the wall is not moving. Okay. So the second mechanism I wanted to tell you about, which is a quite important mechanism to create this turbulent flow, is natural convection. So what is natural convection? So you know that hot gas, hot air is lighter than cold air. And because of gravity, it will tend to move above cold air, okay, by buoyancy. And then there are many situations where the hot is below the cold, okay, like in the atmosphere, for instance. The atmosphere, the atmosphere surface is hotter than the air in the upper atmosphere. And so this is what is called natural convection, in the sense that it's what's happening naturally on Earth. So now if you look at this thing, so for instance, you can get so now you assume that you start from a very sharp interface of hot things and cold things. So the hot is willing to go up, the cold is willing to go down, and basically you are creating this instability, which is exciting again a lot of small scales. Okay, so this is a 3D example. So in 2D, so this was a case when I start with a discontinuity. So now here it's another case where I'm imposing temperature on the bottom and the top. Okay, and typically what's happening is that it's a bit long. So the hot and the cold are tending to create some plumes, so some blobs of fluids, colder fluids or hotter fluids, which are willing to go to the other direction. So this one is willing to go down, this one is willing to go up, and so we have to wait. Or maybe I can go a bit faster. So okay, so it's developing there, and after some time, you see what's happening is that you are mixing hot and white. You start and starting from these small plumes, you see that you're creating much larger structures. So here, for instance, you have a large eddy. Again, here you see a rotating structure, and this is again a mechanism to create turbulence. So here we have looked at cases where we are somehow starting with a boundary or starting with temperature differences, and in my Navier-Stokes equation, I didn't talk about these boundaries or differences in temperature, because now if one is thinking about zooming in a small place here, the flow actually would not care anymore about these specific aspects. Okay, so same, if here I'm zooming here, I mean I have sufficiently mixed the hot and the cold, so that at the end it doesn't really matter if I am cold or hot. What matters is actually that I have a big velocity, that I have many scales which are excited, so that locally one can describe things in terms of the classical Navier-Stokes equation with no temperature, with no boundary conditions when we are close to a wall, etc. Okay, so that's yeah. Same fluid, and just the temperature is different. Yes. No, it's just the temperature. Yes. So they have different temperatures, and the thermal diffusion is very small. So which means that you see that blue will remain blue even if you have sharp gradients between blue and red. They will not mix fast. Okay. And so now yet another mechanism. So now a mechanism which is again involving some inhomogeneities, but this time with just one fluid. So what I assume is that I have a fluid which is sheared. So the top layer is willing to go left, the bottom layer is going right, and I have a sharp interface between the two. And this again will create some instabilities. So you see if you so this one is, so the one was too slow. This one is again too slow. But this is typically what's happening in this shear layer. Okay, so you have mixing between different kind of fluids, but the kind of fluid is just that they are horizontal velocity. Okay, so again, what you see is that you're creating from something where you have just some disturbance at a given scale. So basically, you're exciting many different scales. So maybe it's working. So this one didn't work, no? I'm sorry? No, so now they have the same density. The only difference is their initial condition, where and the boundary condition at infinity, if you want, in the horizontal velocity. So the blue one is willing to go left, and the red one is willing to go right. And this one doesn't work. No, this one doesn't work. Okay, so anyway, so So basically, again, the same kind of instability. So now I'm starting. So you see, it's a periodic domain. So the blue, I think, is again willing to go left. The yellow is willing to go right. Okay, and then we will look in more details to the development of this instability. So basically, this is how the interface is starting to modulate. So this is a zoom. So this thing is a zoom in the white square that you see here. So what you see is that you're creating you're exciting some instabilities, and since this instability are also creating some shear and some things, you see that you have secondary instabilities which are created on the top of that, and you see that you have a full range of scales which are getting excited. Okay, so this is just to show how mature they are with the resolution.
Excuse me. So this is statement that it is more efficient to develop small structures to dissipate kinetic energy. Is this an empirical observation, or is it like we can prove it or something?
So it's both. It's an observation that we can prove. I think that's so basically. So it depends what you mean by proving, actually. So we have there is a theory to explain it, but of course the theory is a theory for physicists. It's not. There is no theorem.
Okay.
Okay, so typically, so this was just to show you some movies, okay, so that now you have an idea of what is turbulence. So let's move now to view and tools. So what I want is to contrast a bit the different views of the mathematicians, the physicist, and the engineer, and somehow to try also to draw some bridges between the different views that are developed. So let me start with the mathematicians. So what the mathematicians like to do, they like to answer by the yes/no given questions. Okay, so a mathematician is proving a theorem. So the theorem is saying if it's true or if it's wrong. It's a yes/no question. So the first question, so they deal mainly with this kind of equations, so just Navier-Stokes, usually with simplified boundary conditions or simplified domain, so compact domain, periodic domain, boundary conditions on the boundary with a smooth boundary, or things like that. So one of the first question is whether or not the problem is well posed. So in what sense? So assume that you start with a smooth initial condition. And the question is whether this solution will remain smooth at all times. Okay? So smooth in the sense of differentiable, for instance. And so even for the Navier-Stokes with viscosity, so us physicists, we tend to think that viscosity is smoothing out everything. So even in the presence of viscosity, there is no clear answer to this question. So the only answer is just a finite time regularity. So if you start from an initial condition, you can find up to what time this solution will remain smooth. But if it's true at any time very large, I mean, this is still unknown. And it's so unknown, while it's a very classical problem, okay, that there is a $1 million prize, which was decided by the Clay Mathematics Institute, which will be given to the person who is able to show that there is global existence and regularity of the solutions to the Navier-Stokes with regular initial conditions. Okay, so this is one kind of question that the mathematicians are addressing. So the second question is, so now assume that we can construct such solutions for finite viscosity. So what's happening to these solutions when you make viscosity to 0? So I told you that the turbulence problem deals with taking very large Reynolds number, so which is equivalent to taking very small viscosities. So the question is, what's happening to that? So now this is more a problem addressed by people doing PDEs, okay, so which are willing to find bounds on on regularity, on some norms of the solution. So the second thing is more a problem of people doing things which are a bit more complicated than PDEs. So PDEs plus something. So it could be PDEs plus probability, PDEs plus some dynamical system like considerations, etc. Or people who are applying tools in order to understand irregular solutions. Okay, because if certainly in the limit of viscosity going to 0, then since you don't have this term which tends to smooth out the small scales, you need to think in terms of weak solutions, in the sense of solutions which are just defined as measures, not as a function. Okay. And so one of the questions is, so assume that we can construct these weak solutions to the Euler equation. So Euler equation is Navier-Stokes with viscosity equal to 0. So assume that we can measure this, construct these weak solutions. Then one question is how to select them, because certainly there are only those which are physical admissible that can be of interest to describe the turbulent things, and in particular those which are corresponding to the limit viscosity to 0. Okay, so this is one notion, is how to select viscosity solutions when you are abruptly making viscosity equal to 0. So the answer is not clear yet. There are some cases where one knows what to do, and I will talk about that in one of my lectures with Burger's equation. Burger's equation, we understand everything. So all these things, they can be reconciled in Burger's. Okay. So then, of course, how irregular are the solutions in the limit of viscosity tending to 0? So in which, so for the mathematician, it means in which space should I look at my weak solutions? And the thing which is related to a question of physicists is, are these solutions enough to dissipate this energy that I have? Okay, so the thing is that, so I will talk about dissipation later, but are these solutions irregular enough? So assume that you don't have any viscosity, you need to dissipate energy, so you need singularities to dissipate it. So I will come back to that tomorrow. And then the thing is, now this is more a probabilistic question. Okay, so assume that, for instance, I take a random forcing, or I take no forcing and a random ensemble of initial conditions. So then you can construct the probability distribution of the velocity field with respect to this randomness. And then you want to understand the turbulent solutions as the measure over the solutions in the limit when you make the viscosity to 0. Okay, so take finite viscosity, construct the probability ensemble of solutions with some randomness, and then you make viscosity to 0. And what you expect is that this measure on solutions will describe turbulent flows. Okay. So these are the questions which are mainly addressed by mathematicians. Now let's move to engineers. So engineers, they are more in the spirit how. So how things are working, how can I model them, etc. So basically, the main questions which is addressed by engineers is to say, okay, I have a flow. Let me assume that this flow, I can decompose it as a mean flow plus a perturbation. Okay, and so now what I define as mean, whatever it is, it could be a time average, it could be an ensemble average over different realization of the flow. So let me assume that I have a way to define the average. And now, so what does it mean to have the perturbation? So the perturbation just means that the average of the perturbation is 0. Okay. So if I take the average of u, I just take the average of u, and because this thing is 0. So now you see that if you make now, if you take Navier-Stokes, so take Navier-Stokes or Euler, and you make the average of this equation with respect to this overbar average,
sorry,
because of, yes.
So this is the case with random driving, is it? Or
it could be the case with random driving.
because I mean, otherwise, what is the average over? I mean,
It could be a time average.
Okay.
So in that case, you will not get that. You will not get this term here.
Okay.
Or it could be an ensemble average, in the sense that, for instance, you take your so assume you take your cup of coffee, you stir it,
Right, yeah.
you remove your spoon, and you look how things is decaying. So of course you have created turbulence. You have a mean flow, which is the mean rotation, but all the small scale structures and the perturbations depends exactly on the full history of your steering. So this is one experiment. Then you take, next day, you take again your cup, you stir it again.
Okay, so it will change a bit, right? Yeah.
So the mean flow will be the same, but the fluctuations will be different. Okay? And then you make an average of all these cup of coffees. So this is over the initial conditions, or over the steering, if it could be steering also. It could be some pumping of energy. Okay? But think that this is very practical. I mean, an engineer, what do an engineer wants to know? He wants to know how much is your cup of coffee mixed, how long it will take to settle, to have no more velocity, okay, and things like that. So the already understanding the average is a big deal. Okay? So now, if the problem is that because Navier-Stokes equation is nonlinear, if you make the average of Navier-Stokes, it's not the Navier-Stokes of the average. Okay, so that, and in particular, because of the nonlinear term, U grad U, if you make the average of U grad U, I mean, you can extract from it average of U dot grad average of U, but you have some remaining terms, okay, that are unclosed and which are basically, so it's called T, like this. Usually it's called the Reynolds stress tensor. And basically it's including all the correlations, the second order correlations of the velocity fluctuations. Okay? So now the main problem of engineer is how to close this term in a consistent manner, or if you want, how to express the Reynolds tensor in terms of maybe the mean, maybe other things, okay, in order to have a closed equation for the average velocity. Okay, so the main problem of engineers is to work on closures of the Navier-Stokes equation. So this equation, once it has been averaged, is called the Reynolds average Navier-Stokes equation. Okay, so again, this is dating back to Reynolds. So Reynolds average Navier-Stokes equations, and so the nickname is RANS, R-A-N-S. Yes, yes, you have it.
The grad P average term will also involve U prime, I guess, right?
So grad P?
That grad P bar,
yes,
that will also involve U prime, I guess.
Yes. In principle, no, not at that scale. So it's no. I don't think so.
By that equation, right? That's again a nonlinear, right?
Yes, or if you want, P bar is not. It might not be the average of P.
Ah, okay.
Okay, but because in the Poisson equation that we write for P bar, you will have a contribution from the mean, the divergence of that, but also the divergence of this one. Indeed, but yes, but this is slaved somehow. It's slaved to what you put. Okay. Yes.
Just to understand, so you have taken all the fluctuation part into the Reynolds tensor.
Exactly. So, or if you want, no, it's not exactly that. Is that I have averaged the equation. Okay, so I have averaged the equation, and then I had to take. So I had the term which was, you see, or because it's very narrow. Okay. So you have that, and so basically when you average that, you basically you have to. It's natural to introduce some u dot grad u, but then you have some terms which are remaining, and these terms which are remaining, basically they are exactly the Reynolds stress. So it's a divergence of so u prime. So okay, that's clear. So now, so one of the questions that the engineer will address is how do turbulent fluctuations are affecting global quantities? So which is, so for instance, the dynamic of U, or maybe the transfer of heat, the mixing length if you have a shear flow, etc. And the thing is that so of course there could be as many models as situations you're considering, but the question is whether you can write models which are working, which are generic somehow, which are working in different cases. So then, so these models, of course, they have to be tuned to do engineering. So they have to be so there has to be a balance between reliability and affordability, for instance. So of course, not doing any model. I mean, you have reliability 100, okay, but affordability 0. And of course, if you just say I do very stupid things, then you can have affordability 100 and reliability 0. Okay, so there need to be a balance, and this balance is problem dependent. So if you want to build the plane, it has to be sufficiently reliable, but not too much, because at the end there is a long experience about plane. You know that they are flying anyway. Now, if you're designing a nuclear power plant, then maybe you have to be a bit more careful on the reliability. See, so I mean everything is tuned usually. And then the thing is that another work of the engineers is to try to understand how to extend things which are usually understood in very simplistic situations. So like you take a homogeneous isotropic flow, you have some results that you get from these simple settings, and you want to know how this can extend to actual flows, to realistic situations. Okay, so this is another work which is done by engineers. Okay, so let me move on. So now, the view of physicists. Yes.
Just to be clear, I mean, see if for example, if I stir this coffee, so in principle, if I did it kind of smoothly, then of course the original equation is sufficient to predict everything, right? Like without the this Reynolds tensor,
yeah, sure.
I should have. But now you're saying if I stir it so hard that it becomes turbulent,
if the Reynolds number is large, yes,
is large, then somehow the original equation is not really. I mean, because small perturbations will lead to different solutions. Is that
exactly.
And that's why somehow I have to include this.
Exactly. That's why you have to make this average.
Okay.
Because you don't want to control all the perturbations you're doing.
Right. Okay. But
so take another example. Assume that you look at the flow above a plate. Okay. So in the ideal settings, your plate is flat. Okay. It has no roughness.
Right, yeah.
So now roughness will introduce some randomness. Maybe it's not exactly flat. Maybe it has some distortion also. So this will again put some randomness.
Right, yeah.
So you don't want to control exactly what's happening with a given plate, because then maybe this plate will be manufactured 1,000 times. So you will have 1,000 different realizations of this plate. So you don't want to control exactly the whole details of each of these plates, but you want to control the ensemble.
Right. Okay.
So the engineers. So engineers, of course, I mean, physicists. I'm sorry. So physicists, they have to understand why. Okay, they have to understand why, but then they are usually limited to correlation functions to understand why. Okay, and so the question is to understand. So again, with respect to some ensemble average that will be specified at some point, they need to understand. So, for instance, endpoint, end time correlation functions. Okay. So one first question that physicists will address is that there are some cases where one can get prediction about these correlation functions from very simple arguments, which are phenomenological, dimensional, etc. And the question is, why is it working? Because it's unclear. I mean, there is no proof, but from time to time, simple arguments are giving pretty good answers. So this is a first question. And somehow it means that if phenomenological or dimensional approach are working, it means that there is some mean field behind which is working well. And so why is this mean field working, and why can we neglect some fluctuations with respect to the mean? So this is the kind of questions that is addressed. And then the second question is, can we get exact constraints on these correlation functions? Okay, so through some conservation laws. So it's not conservation of mass or conservation of energy, etc., but it's more statistical conservation laws, in the sense that it's things which are conserved in average, for instance, with respect to the ensemble average that you are considering. Yes?
When you say that there's a mean field description, it means that there's a description in terms of weakly coupled degrees of freedom?
Yes, there are many different attempts. So turbulence is an old problem. See, the Navier-Stokes equation. So we are celebrating this year. We are celebrating the 200 years of the Navier-Stokes equation. So which means that all the things which have been shown to work somehow in physics have been at some point applied to turbulence, with some success and with some failures. But yes, there are some weak interactions which are possible. And usually this is what people are doing when they are doing weak turbulence. It's called weak turbulence, which is, so it's not exactly Navier-Stokes. It's not exactly what I'm talking about, but it is related somehow. It's a wave turbulence, if you want. Okay, so now so this is one set of questions. Another set of questions is about universality. So we are talking about very different flows with different geometries, with different properties of the velocity field, with different symmetries of the velocity fields. From time to time, something which is excited by boundaries. From time to time, something which is excited by a volumic force. And in all these cases, there are many statistical quantities which are independent of the way we are exciting the flow. So there is a belief somehow that turbulence is universal. But of course, there are no proof. And so the question is to be able to understand these features which are common to all flows. And then there is somehow the hydrogen atom of turbulence. Okay, the thing on which almost all physicists are focusing, which is called homogeneous isotropic turbulence. So its nickname is HIT, like that. So which means that it's turbulence which has no boundary, which is fully homogeneous in space, fully isotropic, and usually maintained in a statistical steady state by some external large-scale forcing. Okay, so that's most physicists are working on this framework. And then, so there is also this sentence which is funny, that it's a legend, I think, that Heisenberg said on his deathbed, something like, "Oh God, why relativity? Why turbulence?" So there is this idea that turbulence is the last unsolved problem of classical physics, and so there are many physicists not from the turbulent field who at some point tried to do something because they had no ideas. So this include, there are hundreds of names. Feynman, I think Feynman started. Then there is a famous guy who was doing turbulence, who passed away 20 years ago, whose name is Krajnan. And so basically he was an assistant of Einstein. So Einstein told him, "Oh, you're smart, you will be able to solve turbulence." And then he did all his career without solving turbulence. Then, so I don't know, so maybe more recently, Polyakov also tried to find some closure on using operator product expansion to use field theory in order to close some anomalous terms in turbulence. and so the thing is that there is this phase of being one of the last unsolved problems, so that this is attracting a lot of people, and a lot of people from different fields. And this is nice, because at the end, you see, it's like if turbulence was a kind of crossroad. Well, people are able to talk together, even if they're coming from very different things. And so it's pretty nice to follow what's happening in the things in turbulence. And of course, still, there is one question. So for instance, many things which were developed for the theory of chaos in the 90s were also stuff which were motivated by turbulence. So everything's connected to spatio-temporal chaos, transitions, period doubling, etc. All these things were coming from turbulence, were motivated by turbulence at least. And the one of the questions that maybe I will come back on it in my last lecture is, can one actually predict this turbulent flow, or is it something which is so inherently unpredictable that at the end all the tools that we have are not able to give the right answer? So this is something on which I will hope to have time to discuss in my next lecture. So let's move to tools. So I mean, this basically I can be very short in that. So the different tools which are used. So now this is again something which is a crossroad of turbulence. So it's a crossroad of different disciplines, a crossroad of different approaches to different disciplines, but also a crossroad of different tools. So there are people doing analytical things in turbulence, but also in turbulence that there are a lot of people doing heavy numerics, very large simulations. And there are also a lot of people doing a lot of experiments. So again, you see, it's something where there is this kind of interdisciplinarity also in the tools. So the analytical tools, I mean, it can be very short because it's I talked almost about everything. So there is all the things related to phenomenology, which is really something coming from theoretical fluid dynamics. So there are all the tools imported from the mathematics of partial differential equations, which are also useful. There are many things coming from chaos and dynamical system, which are used a lot in turbulence. And of course, since it's something where one is willing to get a statistical description, in statistical physics and probability is also having an important contribution, mainly through stochastic processes and large deviations. And with the goals in these analytical tools is, of course, to design models, to give descriptions of universal mechanism by inside simplified models, and somehow to suggest also new measurements or new observable that are motivating experiments. So concerning experiments, so let me start with the oldest method that was used in order to monitor turbulent flow, so which is the hot wire. So hot wire is something like that. So this is a bit complicated, hot wire, but it's something where you have a very thin wire there, you see, conducting wire, and in which you put a current, and then you put this stuff in the flow. And because of the variation of the wind, so there are different heat exchange with the surrounding, which are doing fluctuations to the actual current which is going through the wire. And this is what you measure. And then you have the right formula, calibration, etc., to transform this thing in a velocity signal. Okay. So basically, this is typically the kind of signal that you get. So it's some kind of amplitude of the fluctuation as a function of time at a given position. Okay, and this is typically the kind of experiment you're doing. So you're working. This is something which is done for wind tunnel. So you have a mean flow, transporting fluctuations, and then you sit somewhere and you measure what the mean flow and fluctuations are going through your hot wire. Okay, so this hot wire, you see, is able to measure different components of the velocity. That's why you have different wires in different directions this way. Yes.
This is a fluctuation in the current, right?
Yeah, this is the fluctuation in the current.
And that's because the temperature is varying, or?
Yeah, because the cooling of the wire is varying.
Okay.
It's the heat exchange which is varying because of the wind.
Okay. It's measuring the temporal fluxes.
Exactly. So it's 1 point, and it's a temporal fluctuation in 1 point. So of course, if you can do it at 2 different points by putting 2 wires and separated like this. So basically, the advantage and the difficulties. So in the advantages, of course, you can access very high Reynolds number because you just whatever flow you put. I mean, as long as you have enough time resolution, you can measure whatever you want. Then you can go in any kind of geometries. I mean, you don't care if you have a wind tunnel which is straight or which is a pipe flow, or I mean, you don't really care. But one of the inconvenience is that it requires a mean flow. Okay, because if you want to catch fluctuations, basically if you put your hot wire somewhere and you have no mean flow, basically you will start to affect the flow because you will heat the surrounding air, so it will change all the conducting property, etc. So if you want to have something which is non-intrusive, you need to have a mean flow and to phase the mean flow like that. And then, of course, so it's a single point measurement. And of course, as often in the experiments, you have to massage the data in order to extract a velocity field. So I will talk about Taylor hypothesis. What does it mean? What? This thing? No, it's the current. Yes. So then, so more recently, so mainly because of the facility now to get efficient cameras, digital cameras, etc. So for the last 20 years or so, basically now people are doing image velocimetry of the flow. So so this is an example. So it's a PIV, so particle image velocimetry. So the idea is the following: is that so you have a flow like that. You seed it with particles, with small particles which are not affecting the flow, which are sufficiently small. And then you shed a sheet of laser, this flow, and basically you do you enlighten twice the flow, like that. But your camera is open between during the 2 flash that you put on the flow. So it's recording the 2 positions of the particles. And now from that, you try to correlate these different positions, okay, to maximize the correlation between these positions, so that you can get with what is the highest chance position of one particle with respect to next time. Okay, and from that you construct a velocity field. So usually this is done by coarse graining. So you coarse grain, so you're not looking just at individual particles, but rather at how a blob of particles is changed. Okay, so that you really can compute correlations. So so basically the thing is that so again there are advantages and difficulties. So in that case, compared to the hot wire, you don't need the mean flow. So a problem is that you are just catching things in a plane here. So you have only 2-dimensional velocities in this plane. So you cannot really compute what's happening in the 3rd directions. So even if there are techniques now like so stuff which are called holographic PIV, which are able to get the 3rd dimension, then of course you need to coarse grain because you have to tune somehow the coarse graining scale depending on the resolution of your camera, on how many particles you put, etc. And of course, I mean, if you don't have very expensive camera, I mean, what you get is a rather low resolution image. So this is something. Then another technique, which is called this time particle tracking velocimetry. So before it was particle imaging velocimetry. So what you do now is that you put again particles, but this time instead of just putting this double pulse laser, you shed light continuously, and you use very fast camera in order to track the full motion of the particles. Okay. So this is typically you do that, for instance, in this kind of flow. So this is called the von Karman flow. So you have two rotating fans there and there, which are creating a flow in a turbulent flow in the middle. And typically, what you do is you observe what's happening in this small box in the middle. So this is typically sorry, what you observe for the particles. Okay, and this is once you have to reconstruct the tracks, you can reconstruct the field of trajectories. Okay. So again, so now an advantage is that you can go to very high Reynolds number. I mean, again, if you have fast enough camera, so more money you have, higher is the Reynolds number you can observe. You can go to realistic geometry as long as you can view it. Okay, so of course, if it's blind, you cannot do any imaging. Then now in the difficulties is that usually to track particles for a very long time is very hard. Okay, so usually you can imagine that in this thing you have a mean flow also, and that in this mean flow particles will cross just the observation area very quickly because there is a mean flow. So this mean flow, or if you want a larger scale flow, which can fluctuate, but then the particles will just go very quickly through the observation volume. So doing long tracks is complicated. So doing 2 times statistics is limited. And then, of course, you need again to massage the data because you want to be able to reconstruct the tracks. You don't know exactly, you are losing a track with respect to another from time to time. So from time to time, you have a track going out from the observation volume and coming back. So you see, you have to take care of all these possible bias that you can get in the statistics. And that's it. No, yes, the follow trajectory is hard, but also observing for a long time is hard because typically the machines, the cameras that you're using are doing tens of thousands of images per second. This is the typical thing. So which means that usually you fill up the hard drive the storage of the camera in a very quick manner. Okay, because you're doing a lot of images like that. And so which means that typically a movie that you're doing there is a movie which lasts 3 seconds. So what you do is that you do a movie of 3 seconds, then you download everything, and that's taking a lot of time. Then you do again a movie. So you see, to do long average is hard. Okay. So now let me move to numerics. Oops, sorry. So for the numerics, there are 2 families. So one which is called CFD, like computational fluid dynamics, and this is more the domain of engineers. Okay. So it consists in applying models, closures of turbulence to predict situations, realistic situations. And so basically the idea is to find the large case, so what's happening at the large case and closing the small case. And so now, so I will not go into the details, but the thing is that almost everything which exists in numerical analysis can be applied to turbulence problems. So then you have different ways to represent your domain with different kind of grids, different ways to represent the boundaries. You have different discretizations of the PD that you get. So from finite volumes, finite elements, finite differences, spectral things, or lattice gas, etc. So you have all these possibilities, and then you have different ways to close your equation, to put a closure. So like The usual way you close the Reynolds average Navier-Stokes is by using some eddy viscosity, K epsilon, K omega models, etc. Then you can do large eddy simulations or implicit large eddies, detached eddies, vortex method, PDF method. So, I mean, there is an army of people working on these things. And then you pick any combination of first column, second column, third column, and there is at least one team doing that somewhere in the world and being the specialist of that. Or even maybe there is one annual conference of people doing that every year, you see, in the world. So it's a real big business, these things. And then, of course, usually the people are organized in schools. So for instance, the school of people doing a finite volume will never talk with people doing finite elements. Okay. Not schools, churches will be more appropriate. Okay, so us physicists, what we are rather doing is direct numerical simulations. So direct numerical simulations means that we are exactly solving Navier-Stokes equations up to the smallest case, and with no closure, but then very, very expensive from a computational level. And so for that, basically, we have to use high performance computing. No way other than that. So it's very expensive. And so we have to use local, national, European, international supercomputing facilities. So typically, what most physicists are doing, they are using spectral solvers to solve the Navier-Stokes equation. So what does it mean, a spectral solver? Is that you have Navier-Stokes equation, the usual physicist way to write it. Then what you do is you say, I take the Fourier transform of the velocity field. So if I represent the velocity field as a sum of Fourier components, okay? So why Fourier components? Because then if I want to impose incompressibility, see, the divergence-free condition just means that the Fourier component associated to wave number k has to be perpendicular to k. Okay, so which means that in my 3D Fourier space, kx, ky, kz, if I take some k somewhere, I have a velocity mode there, and this velocity mode as a vector has to be perpendicular to my vector k. So which means that there is no need in that case to solve the Poisson equation. It's just, we just need to project properly the Fourier components. Okay? And then the other thing is that computing derivative is perfect in Fourier. If you want to compute the Fourier derivative, the Fourier of the derivative of u, you just need to take the Fourier of u and multiply by k. That's easy, very easy. So, and for instance, solving the Laplacian is very easy because it's just here you just have a new k square. So it's very simple. So now the thing which is not simple with in the Fourier description in the spectral method is to treat this thing. Okay, so you graduate because it's nonlinear. So if you are doing it stupidly, straightforwardly by just taking the Fourier transform of that, you see that you will get a convolution in k space. Okay, so it's a product, so you get a convolution. So what people are doing, what everybody is doing, is just to go back to real space. So you have u hat, okay? So you compute u hat and grad u hat. You go back to real space. Then you can multiply them because it's a multiplication. And then you come back to Fourier space. So at each time step, at each time you want to compute the u grad u terms, it means that you need to do some Fourier transforms back, forward and backward. And so this, so if you compare to doing the convolution, so convolution means that you need to take all modes, and for one mode, you need to take all the modes such that the sum is giving this mode. So in number of modes, this will be n square operations because it's n times all the possibilities. Fourier transform is just n log n, so which means that it's faster. So these things means that we are doing pseudo-spectral. This is the nickname, so it's pseudo-spectral in the sense that it's not fully spectral because non-linear term is computed in real space. Okay. So now the thing is that with these things, so we are almost doing numerical experiments. So with the highest resolution, we are very close to what is done in experiments, except that the main difference being that now we have access to everything because we have the full field. Okay, so we can measure everything at any time, at the cost of saving it or doing some computation on the fly. But then the problem is that the simulation, we cannot make it as long in time as an experiment. Okay, so usually you have more information, but statistics are less converged. Okay, that's the problem of numerics. But you see, it's a problem, but then it's complementary to experiments. So I can show you a bit so since I will show you data from this code, I can show you this code. So this is the code I'm using.
In the simulation, you restrict up to some certain K modes, isn't it?
Yes, exactly.
Okay.
So since I will come back to that anyway. So the code I will be showing some stuff is called LaTu, like Lagrangian turbulence. It's using MPI. It was designed by Holger Hohmann, who is a collaborator. So basically, up to now, we have been up to 4,096 cube grid points, okay, which means that it's 68 billions of grid points to solve the Navier-Stokes equation. And we have put tracer trajectories, and we had up to 1 billion tracer trajectories. And so basically, this is how the code is scaling when you put it on different numbers of cores. Okay, so these are different resolutions, different colors, like that, and this is the gain in the relative gain in execution speed compared to the 128 running on one core. Okay, and so what you see is that there is some scaling. It's not exactly linear as you would expect if in the ideal case, but it's not too bad. So which means that here, see, compared to the ideal case, we are twice slower, more or less, than what we would expect. But still, it's enough to do big simulations. And you see, so now this is, so I will come back to that in the tutorial. So this is how you vary the viscosity, the number of grid points, time step, of course. And this is the Reynolds number that you get. So you see, from 512 cube to 4,000 cube, you gain a factor, how much is it? 4, more or less, on the, a bit more than 4 on the Reynolds number, so which means that it's costing a lot. Okay. So then, so okay, I will skip that, but because I need to move on. So, third point of my lecture was to give some ideas about the phenomenology of turbulence. So now, what I want to at least to describe, so I will see if we have time to move forward, is the notion of cascade and K41, the Kolmogorov 1941 theory of turbulent flow. So basically, Taylor hypothesis, I will skip it. I will. So let's start from the Navier-Stokes equation. So we start again Navier-Stokes, and let's try to make an energy budget on the Navier-Stokes equation. So we take the equation, we multiply, we take the scalar product with U, and then we make a space integral so that we have the global energy in our domain. So let's look at the different contribution of the various terms. So the first term, so this one, of course, will give time derivative of energy. So this term, which is written here, because of incompressibility, we can rewrite it as an exact gradient this way. Okay. So as it's an exact gradient, see, it's just the integral of dj of, I'm sorry, I think that there is it should be ui here. No, it's dj uj, I'm sorry. So dj uj, like that. So if we have no boundaries, so assume that we are living in the periodic domain, for instance, this will be 0. Okay? So this term is conserving energy. Now pressure is the same. So pressure, you see, you have U, so this is U dot grad P. Then you make, since your flow is incompressible, you can put UI inside the DI, okay? Because DI UI is 0, yes? No, I'm sorry, the cross is a scalar product. I mean, here I should have put dot. It's a scalar product. And so now again, you have an exact gradient. So again, this term is preserving kinetic energy if you have no boundaries. So now let's look at the viscous term. So of course, the viscous term is supposed to dissipate. So you write it. So you make some massage by integrating by parts. And what you can see is that you can write it as minus viscosity times something which is positive, always. So forget about the contribution from boundaries. So which means that this term is always dissipating energy. And now, of course, you have forcing, so the forcing is doing some work. So now, which means that somehow, if you look at this homogeneous and stationary turbulence, okay, so now assume that your energy is preserved as a function of time. This means that the viscous term here and the external forcing, so the input and the dissipation, they have exact to balance in an exact manner. Okay, that's fine. So energy budget is simple. So now the thing is that if you so remember dissipative term is written this way. So let me which is the same as that. So dissipative term is something like viscosity times gradient square of the velocity. So now assume that we take the limit of infinite Reynolds number. Okay, so which means that we make viscosity to 0, for instance, by keeping injection rate and scale fixed. Okay, so we have the same steering and we tune the viscosity to make it equal to 0. So because we have this equality here, it means that necessarily we have to have this dissipation of energy going to a constant. Okay? Because the only way you dissipate energy is through the viscous term. So the viscous term has to adapt itself to the fact that if you have a steady state, if you don't pile up energy, okay, you have to maintain a finite dissipation of energy, even if the viscosity is going to 0. And this is what we call the dissipative anomaly in turbulence. Okay, so this is the main effect of turbulence, the main thing, the main motto or belief or axiom extra of turbulence, which is that dissipation is independent of the Reynolds number. And the highest at Reynolds number going to infinity, dissipation has a finite limit. Okay, so these are some sample of numerical experiments which are showing this dissipation properly rescaled as a function of the Reynolds number. And what you see, and you see that the Reynolds number is growing up to 10 to the 5. And what you see is that indeed, when you make Reynolds number larger and larger, you always go to a constant. Okay, with a dissipation which becomes independent of Reynolds number. Okay, so this is the first axiom of turbulence. Yes.
Just a quick question about how the limit is taken. So nu times u, I mean, u has to be scaled in a certain way so that nu times u is going to a constant.
So basically, you have to scale. No, so basically, what you have to scale is to account for that. In this, what is scaled here, the scaling that you use on the graph is just to account for the fact that you want to compare different simulations or different settings with different injection. So you have to write it in dimensionless units.
No.
But then if you assume that you fix that, okay, you don't have to do any rescaling in order to have this going to a constant. If you prefer, if you make nu to 0, gradient of u has to become infinite. Okay, so you have to have a singularity at small scale. You have to create bigger and bigger gradients.
Okay. Capital L is the length at which you're driving it.
Exactly. Yes.
What is the capital U here? The
what
capital
is
U?
The what? I'm sorry.
U. It's your y-axis level. Epsilon dy u cube.
U cube is the typical scale of your energy injection. U square will be the typical velocity at which you're steering. Okay, the typical energy that you inject. So if you want, U cube divided by L is epsilon I. Okay. Yes, I should have put epsilon I here. It would have been easier. Okay. So now what it means? So it means so having this going to 0 and this remaining finite, it means that you're creating smaller and smaller scales. And this is how a turbulent flow looks like. So what is shown here is the local dissipation. Okay, so it's the thing that you need to average in order to get the global dissipation. So what you see, so this is typically the scale at which you're injecting the energy in this simulation. So this is a slice of a 3-dimensional simulation. And now if you zoom inside this, you will see that basically you're creating very thin structures where energy is dissipated. Energy is dissipated, you see, on filaments there, which are basically at the smallest scale of your flow. And you see that you have variations on such small scales. So you're creating thinner and thinner structures when you increase the Reynolds number. So now how to interpret that? Okay, so this is the idea of Richardson cascade. So Richardson cascade, this year we are celebrating the 100 year of, so it's 200 of Navier-Stokes, 100 of Richardson cascade. See, so it's just halfway from Navier-Stokes. so basically the idea is the following: is that you're injecting energy at large scales. Okay, so assume that you have a stirrer like that. This energy, so for instance, is creating smaller eddies because of one of the mechanisms I showed you. So like the shear flow, for instance. So you have a big eddy, two big eddies, and in between the two, you have some instability, which is creating smaller eddies. And this continues downscale up to a given scale where things are dissipated. Okay, so you have a cascade of instabilities and with a flux of energy, which is such that the injection of energy is equal to the dissipation. This is what we want to get in order to have a steady flow, a steady state.
Just one question. Like,
yes.
What is this smallest length scale at which?
It will come. It will come. It's so the smallest length scale depends on viscosity, and I will show it to you. Not now, but next slide. So now let's assume that we are doing the following reasoning. So let's say that we define as UL the typical velocity at a given scale L. So that UL squared is the content of energy at that scale. Okay? And then what we need to assume also is that typically, you remember that these two terms, they are coming from the material derivative of the fluid element. So what is typical in flow is that these two terms are of the same order. Okay, so that time derivative is like U grad. Okay, so what does it mean that time derivative is like U grad? It means that 1 over time is like length divided by velocity. I'm sorry, 1 over time is like velocity divided by length. Okay, so which means that the typical time is just the turnover time. So at a given scale L, I have UL as a typical velocity, and then the typical time scale will be L divided by UL. Okay? So now let me assume that I'm coarse graining of a different scale in order to see how this energy content is varying over scales. So now, what you say is the following thing, is that you say that the energy UL squared, which is contained at this scale L, is increasing because it's receiving energy from larger scales. And the rate at which it increases is, so basically you have no choice. It has to be the UL squared divided by tau L. You see, basically it's coming from this equation. You cannot do anything else. Okay, so you have a typical time scale, a typical amplitude of energy. So the rate of increase of energy has to be given proportional to these things. So to U squared divided by tau, which is the same as U cubed divided by L. And then it's transferring with the same rate to smaller scales, or it's dissipating because of viscosity. So now if you want to know the rate at which you have viscous dissipation, so now you have to put something proportional to nu. Okay, so in principle it should be nu UL squared. So it should be, because it's, I don't have it here, it's nu times Laplacian of U times U. So it's like U squared divided by a square length. Okay, or you can just think in terms of dimensional analysis. Okay, so now the thing, yes. So basically the ratio between these two stuff, okay, is again a Reynolds number, but this time this Reynolds number is scale dependent. Okay, so it's as usual L times U divided by nu, but this time where you put the UL at the right scale. Okay, so the idea now is to say that as long as this Reynolds number, scale-dependent Reynolds number is large, I'm having instabilities, I'm chaotic, and I transfer to smaller scales. Okay, so this is the idea of the cascade, is that you have an energy content which depends on scale, that the Reynolds number, this time, that you can balance at the given scale the injection and injection, transfer, and dissipation, and that as long as the ratio between these two things is large, you transfer to smaller scales. So now, yes.
The last statement, I mean, no, what was this? So, what is the last statement? I didn't. Can you say the?
That basically you can define a Reynolds number which depends on scale. And as long as this Reynolds number is very large.
Reynolds number at the scale L is defined as ratio of energy flow in and rate and the dissipation.
Exactly.
Rate.
Exactly.
And then what was the statement for Reynolds number much greater than 1? The flow is.
Yes, the flow is unstable. And so basically it's transferring to smaller scales. It's creating smaller eddies.
Oh, because
because it's too large, because the dissipation is not enough.
Okay, so that's why it becomes unstable and develops smaller.
And it's creating smaller L.
Okay, and it will stop developing
when this term is 1, exactly. So now this is the so now there are some cascade hypotheses. So I need to hurry up a bit. So basically the hypothesis has the following. Okay, so these are the hypotheses in order to understand Richardson cascade and Komrogov theory. Is that there are, in a given flow, so let's take our homogeneous isotropic flow. So we have only 3 parameters which are characterizing our flow. So the scale at which we inject energy, how much energy we inject, so what is the typical velocity at this injection scale, and the kinematic velocity of our flow. And this is how we define, so it's 3 parameters, which and only 1 non-dimensional number, which is the Reynolds number at the large scales. Okay, so turbulent flow is is characterized by 3 physical parameters. There are 2 dimensions, space and time. So we use the pi theorem, Buckingham pi theorem, to say that it should depend only on 1 dimensionless parameter, which is the Reynolds number. So now the second thing is that we have this dissipative anomaly. That typically this epsilon, which is both the injection rate, the dissipative rate, the transfer rate between scales, etc., is becoming independent of the viscosity when we make Reynolds very large. Okay, because it's going to a constant. So which means that the only way we can write down our dissipative term, okay, since it's independent of viscosity, we have only these 3 things. So we do again dimensional analysis. So we have to build something which is like a dissipative rate, so something like meter square per second square per second. Okay, so meter square per second cube. We have to construct it with U and L only, without nu. So which means that dimensionally, it has to be like U cubed divided by L. Okay, so this is the next step. So then there is this notion of local isotropy, so which was introduced by Kolmogorov, so now in 1941. So is that when this local Reynolds, this large-scale Reynolds number is large, and we are far enough from the boundary, we can say that our statistics are homogeneous isotropic. So this is this thing. And so now we distinguish between 2 ranges of scales. So the inertial range, so for scales which are smaller than injection scale and bigger than this cutoff scale, where basically the statistics are independent of nu, but depends only on L and epsilon. Okay? And then the viscous range, where the Reynolds number, local Reynolds number is small, where the statistics depends only this time on nu and epsilon, and no more on the scale, because it's small scale, so everything is smooth, so there is no scale dependence. Okay? So these are the main ingredients of Kolmogorov 1941 theory, or if you prefer, Kolmogorov self-similar theory. So now we are going back to these things. So we know that we think that kinetic energy is cascading from large scale to the small scale with a constant rate. This constant rate is giving like this, and it's given also by this UL cubed divided by L. So at any scale L, assuming that this thing, that we are in the inertial range, Reynolds number is large, statistics depends only on L and epsilon. Okay? So at that scale, basically, the only way we can write down the typical velocity is by saying that, okay, so the rate should be like U squared divided by the typical time, or it should be like U cubed divided by L. And this means that the velocity has to be like epsilon times L, everything to the power 1/3. So again, it's just dimensional analysis under the hypothesis of the previous slide. And now you can write down the scale-dependent Reynolds number, now that you know how things are scaling as a function of scale, how the velocity is scaling. So the local Reynolds number is UL times L divided by nu. You replace UL by this expression, you have something like this. And this is nothing but the large-scale Reynolds number times the ratio between small and large scales to the power of 4/3. Okay? So then what we said is that this is true until this local Reynolds number is becoming order unity, as long as it's large. And when is it becoming unity? It's becoming unity at the scale which we call the Kolmogorov dissipative scale, that is called eta, and which is such that this Reynolds number is 1. And then from this, you get that this eta scale is a given function ratio of powers between the viscosity and the dissipation rate. So now you see that when you make take dissipation finite viscosity to 0, you get that the small scale is going to 0, of course. Okay. So now I will finish here. So there will be several examples which are illustrating the relevance of K41 that I will give in the tutorial. So that basically this is the thing. So of course in the tutorial I'll be happy to answer questions and to show you how different quantities can be extracted from this dimensional analysis a la Kolmogorov. Okay, thanks. I will stop here. Any last question? But I'm already late.
So this is the length scale at which dissipation occurs.
Exactly.
So does it mean like if I look at the flows, they have kind of sharp fronts which have.
I will show everything
on this.
Yes. I will show everything tomorrow.
So like in the beginning of the talk, you showed that this turbulent flow has self-similar structure, same structure at all scales. So can we see that from Navier-Stokes equation?
So basically, this is what you see as a self-similar structure. So somehow the typical velocity fluctuations that you will observe at a given scale,
yes,
you see, they are just scaling as a power of the length. So which means that if you want, look at these things, is that epsilon is independent of scale, and that u cube divided by L, if you take this ratio, then it's becoming independent of scale. Okay, so then I will show you tomorrow how you can extract that from different statistics. Like, so the spectrum I will show it during the tutorial. And tomorrow I will show different statistical quantities which are telling you why it's, that are confirming that it's almost self-similar, but it's not exactly self-similar.
This one also, as you said that when nu goes to 0, this grad u should diverge, right?
Exactly.
So now we can also see from the scaling.
So gradient is something like that. Agree? So now if I replace UL by epsilon to the 1/3, L to the 1/3. And so it's something like epsilon 1/3, L to the -2/3. So this is how gradient is, more or less. Did I do something wrong? No, this is U by L. Yes. So now you want to compute the typical viscosity. The typical dissipation, which is nu times, let me put grad u square. Okay. So this gradient, you have to compute it as this stuff at L equal to the smooth scale, to the smaller scale of your cascade. Okay, so because you see that here it's not differentiable, because U is going like L 1/3. So if you are too large case, you cannot compute gradients. You have to go to scale equal to eta, to this cutoff scale. So which means that this thing, you see, will be something like nu times the square of that. So epsilon 2/3. Why do I have 2/3? Eta. You agree with that? 4/3. Okay. And now I replace eta by this value. So eta minus 4/3. minus 4/3 of 1/4. Minus 4/3 of 1/4, so minus 1/3. New minus 4/3 of 3/4. So there is something wrong. Maybe this sign, no? Okay, and so it's indeed epsilon. This is answering your question.
Yes, so I guess we stop here and then again meet at 4.